Hello again, it is Miss List, and today we are looking at 7.7, which is calculating the equilibrium concentrations. So out of all the sections on equilibrium, this one seems to be the one that can give students fits. One way to approach solving these types of problems is by creating what's called an ICE table. This is not the only way to solve these types of problems, but it is a way for us to organize the information in a meaningful way. I stands for initial, C stands for change with coefficients, and E stands for our favorite word, equilibrium. So when we approach a problem, we are going to organize all the information that's given to us by creating an ICE table. The best way to do this is to start looking at some examples. So example number 1 says, given the following reaction, if your initial concentration of A and B is 1 and the equilibrium concentration of C is 0.12, what is the value for Kc? First, we're going to start by writing our equilibrium expression. We always do products over reactants, C to the 4th power, and then my reactants are A and B would be squared. Then I'm going to fill in my ICE table with my known information. So I have my chemical reaction written across the top, and then I have ICE down the left. And remember, ICE stands for initial, change, equilibrium. So I know my initial values for A and B are 1. It tells me that in the problem up here. And it says the equilibrium concentration of C is 0.120. What I'm going to do is now figure out how each of them changed. I actually wrote that in the wrong spot. I needed to write for the 0.120 is what the equilibrium concentration for C is. That should actually go down here at 0.12. E stands for equilibrium. I know that at the beginning of the reaction, C is going to be 0. And so that means that the change that it increased by would be 0.120. If it started at 0, then it had to go up by that amount. Now, we're going to use that to now figure out what happened with A and with B. For B, it's going to decrease by some amount. And what I notice is we have to take into account the coefficient. That's why up here it says C stands for change with the coefficient. The coefficient for C, product C, is a 4, but the coefficient for B is a 2. So that means it's going to change twice as much compared to B. So if C went up by 0.12, then B is going to decrease by 0.06. And again, I figured that out by looking at the mole ratio. Similarly, if A has a coefficient of 1 and B has a coefficient of 2, that means B is going to change twice as much. So A is going to go down by half as much as B did, or by 0.03. Now that I have my equilibrium values, I can plug them into my K expression and get my actual value for K, which is what they wanted me to do. So I'm going to plug in the 0.120 in for product. My 0.97 has no exponent because A had no coefficient, but 0.94 does have a coefficient of a square. So I plug that into my calculator and I get K equals 0.000242. Let's take a moment and just think about what we did and go back over the process. So the first thing I did was I filled in the ICE table the information that I already knew and that was given to me in the problem. The information that was given to me in the problem was the concentration of B and then the equilibrium amount for C. I know at the initial point of the reaction at the beginning that there would be no product. And so that means that C would be 0. From that, that tells me that C increased by 0.120. And what I did is I used the mole ratio to figure out if C is increasing by that much, how much would B decrease and how much would A decrease. And then I actually perform that subtraction. 1 minus 0.03 gives me the 0.97 and 1 minus 0.06 gives me the 0.94. Once I have all those numbers at equilibrium, I can plug them into my equilibrium expression and solve for K. You might be thinking, that wasn't so bad. Well, it can get a little bit more complicated, and that's what we're going to see here on this next example. This time they give us the K value, and it says if given the following reaction with the equilibrium constant of 3.4 times 10 to the negative third, if 1 molar A and 2 molar B are allowed to reach equilibrium, what are the equilibrium values? So in our first example, we were looking for K. This time they give us K, and we're going to try and figure out what the equilibrium values are. So as always, we are going to start by writing our equilibrium expression, products, over my reactants. My next step is I'm going to fill in the information that's given to me in the problem. It tells me that A is 1 and 2, or B is 2, and my product, AB, should be 0 initially. The fun part here is that I don't know how much it's changing by. So I'm going to let that equal x in my equation. So this is going to increase by some value x. This is going to decrease by some value x. Same thing with A. This is going to decrease by x. I didn't add a coefficient, or none of these have coefficients in them, which means it's a 1-to-1 mole ratio. So they're going to decrease by the same amount. In our previous example, I had adjusted the change amount based on the coefficients, but in this one, since the coefficients are 1, then they're going to go down by the same amount, which is minus x. Now, from here, we can use our 3.4 times 10 to the negative third equals x over 1 minus x times 2 minus x. Unfortunately, if you are keeping track at home, that means we would have a polynomial here in the bottom that we would need to distribute. And that would turn into us having an x squared value, which is a quadratic. And that can get kind of complicated with the math. So there are two schools of thought. One thought is to use NSolve on your calculator. Many of my students have calculators that have NSolve on them. If you know that your calculator has NSolve on it, if it's a TI graphing calculator, it does. You would just need to learn how to put these values into NSolve. My advice would be to ask one of the math teachers. They likely know how to do it, or I'm sure there's videos out there that tell you how to put this in for NSolve. The other way is what we call an assumption-based calculation. Using the assumption-based calculation, we assume that because K is small, that means that the reaction is not going to go very much to completion. And that means that X is likely going to be an extremely small value. If X is an extremely small value, then we can assume that it's negligible. So what that means is I can rewrite this as 3.4 times 10 to the negative third equals X over 1 times 2. That makes the math a whole lot easier to solve for my answer. If you do it this way, you get X equals 6.8 times 10 to the negative third, which is the same as 0.0068. If you do it the NSolve way, you should get an answer that is very, very close to that. Example number 3, it tells us that the initial pressure of nitrogen is 1 and hydrogen is 2, calculate the Kp for the following reaction if the value for NH3 is 1 at equilibrium. So similar to what we've done before, I'm first going to write out my K expression. Product is NH3, and it is squared over N2 times H2, and H2 would have a cube. I'm going to set up my ice table right underneath my chemical reaction, and I'm going to fill in the information that I know already. So it tells me that the initial pressure of nitrogen is 1, the initial pressure of hydrogen is 2. I know that the initial pressure of my product should be 0 because at the beginning of the reaction, no product has been made. And it tells me that its equilibrium pressure is 1 atmosphere. So the change would be that this one increased by 1.0. This is where we start to look at our mole ratios. Nitrogen has no coefficient, but NH3 has a coefficient of 2. So that tells me that if NH3 went up by 1, NH2 is going to go down by half as much. And if you wanted, you could do a little mole ratio to help that out. But this one's going to decrease by 0.5, which means at equilibrium it's 0.5. For hydrogen, hydrogen has a coefficient of 3, and nitrogen has a coefficient, or excuse me, my product has a coefficient of 2. So for this one, working out the mole ratio, that tells me that because of the multiplying it by 3 and then dividing it by 2, that means the change for this one is going to be 1.5. So 2 minus 1.5 is 0.5. From here, I'm going to plug them into my K expression and then solve for K. So in the top, we get 1 squared. In the bottom, we get 0.5 cubed. And I type that into my calculator, and I get a K value for the equation as 16. Example number 4, we have a reaction of H2S goes to H2 plus S2. They give us a K value, and they want us to find the equilibrium concentrations of H2 and S2. So let's start with our K expression. My products are going to be H2 and S2. H2 gets a square, and then my reactant is H2S, and it also gets a square. I'm going to rewrite the equation down here and then set up my ice table right underneath of it. It says that the 5 liter or 0.5 liter reaction vessel initially contains 0.0125 moles. So I'm going to first change this into molarity. Molarity equals moles, 0.0125 moles over 0.5, which would be my liters. So this ends up being 0.025. And that's my initial concentration of this, 0.025. My hydrogen gas and my S2 are going to be 0 at equilibrium. So this is similar to example number 2, where I'm trying to figure out what the equilibrium values would be. So I know that this one is going to increase by some value x, so that's x. But because of the coefficient for hydrogen, that's actually going to increase by twice as much. And then H2S is going to decrease. It has the same coefficient as hydrogen does, so it's going to decrease by 2x. Now that I have my equilibrium line filled in, I'm going to use the K value, 1.67 times 10 to the negative 7th. And I'm going to plug in my equilibrium values into the equilibrium expression. So 2x was hydrogen, and that gets squared. X is for S divided by 0.025 minus 2x, and that is also squared. So the math here gets tricky, just like we saw in example number 2. There's 2 thoughts with this type of problem. Again, you can type this into nsolve on a graphing calculator and figure out the value for x. But similar to what we did in number 2, because K is so small, I can assume that X is going to be very small. So I'm actually going to get rid of that minus 2x in the bottom. And if I do that, this makes it a much more manageable problem. I can rewrite it as 1.67 times 10 to the negative 7th equals 2 squared is 4. And then I have x squared times another x. So that's going to be 4x cubed over 0.025. I'm going to multiply on both sides by 0.025, so that cancels. That gives me 1.044 times 10 to the negative 10th equals 4x cubed. Divide by 4, and then I can take the cubed root to get x by itself. If you do that, I get a value for x equal to 0.000297. So as I'm working these out, I'm showing the assumption-based solving method. Again, you could put this whole equation into a graphing calculator and have it solve it for you. The assumption-based method is a little bit easier, I think, assuming that because K is small, that X is also going to be small, and that makes the math a lot more manageable. Although if you are calculator savvy, the nsolve can really help. Okay, example, we have a sample containing 0.5 of X is placed into a small system, or is placed into a system and allowed to reach equilibrium. The concentration of X at equilibrium is 0.35. Calculate the value for K. So K is going to equal y cubed z to the 4th divided by x squared, products over reactants. Get my ice table set up. Initially, it says we have 0.5 of X, and at initial, we're going to have 0 and 0 of our products. And it says at equilibrium that X is 0.350. That means it went down by 1.5. If that went down by 1.5, or sorry, 0.15, if that went down by 0.15, that means that my products would increase by that same amount if they had the same coefficient. But I notice that my Z product has a coefficient that's twice as big. So that means it's going to increase not by 0.15, but by 0.3. And that's because of the coefficient. It's a 4:2 mole ratio. For Y, I notice that it has a coefficient of 3. So it's a 3:2 ratio. Or you can think of it as it's 1.5 times bigger. So like if I took 2 times 1.5, I'd get 3. And so I need to multiply my change by 1.5. And if you do that, you get 0.225. From here, I'm going to plug them into my equation. So y, which is the 0.225, is going to get cubed. Z, which is the 0.3, is going to go to the 4th power. And then the equilibrium value for X is 0.350, and it gets squared. Math happens in my calculator, and I get a K value of 0.000753. Okay, I know that was a lot of examples, but this is probably the most challenging of the sections that we've covered so far in Unit 7. And we will be using ice tables to set up problems in Unit 8. So it's pretty important that we understand what's going on in this. Keep in mind that every problem is going to look a little bit different as what's given versus what we're trying to find. The ice table is just a way for us to organize the information and to think about what is happening in the reaction as far as what's changing from reactants to products. Thanks for listening. I will see you next time for 7.8.